Hey there everyone. Today we're doing Descartes' rule of signs. This is section 4, day 2. Descartes came up with a rule that will help us determine exactly what types of zeros we have in our polynomials. And it's a pretty simple rule. Basically what you do is you're going to find the number of variations in the sign of the function. Okay, what we mean by variations is whenever one term is negative and then the next term is positive, or vice versa. So I always look from left to right across the polynomial, and we're going to count the sign changes. So the first part of the rule says that if we count the number of variations in the sign change of f of x, that will tell us the number of positive zeros, at least the real ones. Okay, it could be that many or some number less than that by even amounts. So in other words, if we found there were 6 sign changes, then there are either 6 positive, 4 positive, 2 positive, or no positive real zeros. Okay, so it's always some amount less than that by 2's. So if we found out that there were 5 variations in the sign change, then there would be either 5 or 3 or 1 positive real zeros. Okay. To do the negative real zeros, you're going to do the same exact thing, but instead of doing the number of sign changes for f of x, you're going to do the number of sign changes in f of negative x. So once you get the process down, it's pretty simple. Let's start with example 5, where g of x is given as negative 3x cubed plus 2x squared minus x minus 1. And so we want to look from term to term and see how many times we change signs. So our first term is negative, our second term is positive. So that counts as our first sign change. So I was just kind of number them, 1. And then we go from plus 2x squared to negative x, so that would be a second sign change, 2. And then this doesn't count as a sign change. We have negative x and negative 1. So these two terms are both negative, so that's not a sign change. So this means that we have 2 or 0 positive real zeros. Alright, and that's pretty useful. That lets us know that if we find 2 positive real zeros, there are no more left to find on that side of the x-axis, that the rest of them will be negative. Let's see exactly how many negative ones there are. So now we need to modify the function a little bit. For negatives, you got to do g of negative x. So we're going to plug in negative x for all of our inputs. That's negative x cubed plus 2 times negative x squared minus negative x minus 1. We want to simplify this first so we can see the sign changes. Negative x times negative x times negative x is negative x cubed, times negative 3 is going to be positive 3x cubed. Negative x squared, that's positive x squared, so this is positive 2 times x squared. Negative negative x, that becomes positive x. And then our minus 1. So really quickly we can see that our first 3 terms are all positive, so there's no sign change until we get to our constant. So there is one sign change down here. And so because there's one sign change, that means we have 1 or some number by 2 is less than that. Well, there's no other numbers less than 1 by 2, so that's it. That means there's exactly one negative real zero. Okay, so when they ask you to describe the possible real zeros, this is how you're going to do it using Descartes' rule of signs. Alright, try that on your own for these two problems. I'm going to put the answers up now, so hit pause if you want to keep trying it on your own. Okay, if you did it correctly, you should have noticed that there was one sign change in 5a, so that means there's one positive 0. Once you plugged in h of negative x, then you got that there were 2 sign changes, so there's either 2 or no negative zeros. For 5b, there were 3 sign changes. I marked them all. So that means there's either 3 or 1 positive 0. And then when you plug in negative x, there's only one sign change. So there's only one negative 0. Okay. That's using Descartes to describe possible real zeros of polynomial functions. The last thing we're going to do in this section is something that utilizes what's called the conjugate root theorem. The conjugate root theorem says that anytime a polynomial equation has a root in the form of a plus bi, then that means that the opposite or the conjugate complex number a minus bi must also be a factor. So if I tell you one of the factors of my polynomial is a plus, or we'll actually use numbers. Say I say that one of my factors is 2 plus I. That means I have to have its conjugate as well. So 2 minus I automatically becomes one of the factors. One can't exist without the other. So using this concept, we can actually take linear factors and change them into polynomials. If you have a list of all the factors of a polynomial, you can rewrite those. Sorry, if you have a list of roots, you can change those roots into factors. So if I give you a list of factors, C1, C2, all the way up to C to however many, you can rewrite that as x minus C1 times x minus C2, so on and so forth, and then FOIL that to recreate the polynomial. That's exactly what we're going to be doing in example 6. So the important thing to remember is that when you have the roots, or you have the zeros, that you're subtracting them from x to get your factors. So for example, if negative 2 is one of my zeros, I want to make sure that one of my factors is x minus negative 2. Now most of us can do that in our head and simplify that to x plus 2. But it's generally good practice to remember that we're actually subtracting the zeros from all the x's, and you'll see why that becomes important when we do the imaginary complex ones. So for the other one, it's going to be x minus 4. That one's pretty easy, not much to simplify there. It's going to be another factor. And now we have our first complex factor. So if 3 minus I is a 0, that means that its conjugate, 3 plus I, also has to be a 0. And so we need to write two factors now, one with 3 minus I. So again, you do x minus, what's the complex number? 3 minus I. Keep that in parentheses. You don't want to distribute the negative and make this more complex. So we're going to keep that bunch together. And then we're going to do the same thing, but we're going to subtract x minus the complex number 3 plus I. So remember, these complex numbers, you don't want to break them up until we start getting into the real distribution part. Keep them bundled together as long as you can. Alright, so now we're going to FOIL. X times x is x squared. X times negative 3 plus I is negative x times 3 plus I. Negative 3 minus I times x is negative x times 3 minus I. And lastly, we have negative 3 minus I times negative 3 minus I. That's going to be a positive 3 minus I times 3 plus I. Okay. So we're still foiling. We still have our 4 terms that we get when we FOIL. They just look a little more complex because you're multiplying a variable times a complex number. But in this next step, you'll see how much actually cancels out, and this simplifies down very quickly. So I'm going to just combine. Well, first distribute. Negative x times 3 is negative 3x. Negative x times I is negative ix. Negative x times 3 is another negative 3x. Negative x times negative I is positive ix. So notice that these imaginaries are going to cancel out, and if they do, then you know you're on the right track. They should always cancel out. And then we're going to have to FOIL this at the end here. So 3 times 3 is 9. 3 times I is 3i. Negative I times 3 is negative 3i. Again, they should cancel out. That lets us know we're doing the right thing. And then negative I times negative I is negative I squared, which will change back into a real number. I squared is negative 1. So this becomes 9 minus negative 1 at the end. The x squared is still here, and we have minus 3x is minus 6x. So now we get a nice pretty trinomial. This is x squared minus 6x plus 10. Remember that minus minus 1 is actually plus positive. So we get negative 6x plus 10. Now we might as well go ahead and FOIL this part over here. So we're going to get x squared minus 4x plus 2x. That's going to be minus 2x minus 8. And now that we have two quadratic trinomials, we can FOIL these. X times x is x to the 4th. X squared times negative 6x is negative 6x cubed plus 10x squared minus 2x cubed, doing the second term now, plus 12x squared minus 20x, and then the last term, minus 8x squared plus 8 times 6 is 48, 48x minus 80. And we just combine our like terms. So x to the 4th, I'm going to combine these two. Minus 6x cubed minus 2x cubed is minus 8x cubed. Let's see, 10x squared plus 12x squared is 22x squared. Whoops, and there was a third one I missed over here. Minus 8x. So I'll go ahead and combine all those. Let's see. 10 plus 12 is 22, minus 8 is 14 x squared. And then minus 20 plus 48 is going to be plus 28x. And then, of course, the minus 80 at the end. So there's our polynomial function. This polynomial function has all of the zeros at negative 2, 4, 3 minus I, and 3 plus I. Okay, let me give you one to try on your own. There's 6a and 6b. It's pretty much the same thing we did before. One thing to note is that we have a multiplicity here. So if they tell you that there's a 0 with multiplicity, how many times should you make it a factor? Well, the exact number of times the multiplicity is. So real quick for 6a, we'll get you started. This is going to be x minus negative 3 and x minus 1 twice. So you can either write it like x minus 1 squared like this, but since we're going to have to FOIL eventually anyway, you might as well just write it out as x minus 1 times x minus 1, because you got to do it twice. And then 4i is our complex number, so we're going to have x minus 4i. But don't forget that we also have to have its conjugate. The conjugate of 4i would be negative 4i. So anytime you have imaginary or complex numbers, their opposites also have to be. So we also have x minus negative 4i. Okay, that's more than enough to get you started. Make sure that you FOIL the common ones together first. So I would FOIL the imaginaries and then go ahead and FOIL these squared binomials. And then try 6b, of course, as well. Okay, so looks like a lot of work, but if you organize it, it's not too bad. Make sure that, again, it's a lot easier if you FOIL the ones that are similar first. So x minus 1 times x minus 1, that simplifies down, and then distribute from there. And again, always do your complex ones together, and make sure you keep them separate. In other words, don't try to distribute this minus sign into the 1 plus I. It's going to make it more complex. Instead, just FOIL them as one term. So x times x is x squared. X times negative 1 minus I is negative x times 1 minus I. Leave that here until this step, and then distribute the negative x. Okay. We'll be going over this a little bit more tomorrow. Here are the classwork problems if you wanted to get a little bit of a head start on them. You're doing 26 through 31 all. You're just using Descartes' rule of signs on these. 33 through 47 odd. The 33 through 41 are like what we just did. You're given the zeros and you're to write the factors and then distribute. And then 43, 45, and 47. It's kind of a combination of what we've done. You're going to be listing all of the zeros for these factors and using Descartes' rule and rational root theorem to help yourself find them. Okay, that's it. We'll see you tomorrow.